They don't change it from AC to heat real quick, so
Gotcha. All right, gentlemen. Monday, October the 30th, we're session 7 in our book, starting on page 37, section 3.0, 3.7.0 to the end of the chapter. We will go over tonight marinas and boatyard calculations, farm load calculations, and motor circuits. We will go over the review in the green that you had for homework, right? And then we will try to go over review questions. I didn't know those did that. That mine don't do that.
this one is just really low on that
Cool.
side.
Okay. All right, so that's what we'll do tonight, and then, so next week, we'll try to review some if we need to, and we'll have a test on module 1, which is feeder loads and calculations. So that's where we're at. So let's look at my safety review and see what we want to review tonight. I think I know what it is, if I remember right. So, thinking about what we're going to be looking at tonight as far as boat yards or marinas or farm. Anybody ever worked on a marina or boat yard? Probably not. Not around here. But on a marina, you might would have a chance to work on something like at Hartwell, maybe, which I have done on piers down there. Which the rules are governed by the, my mind just went blank, who governs it? I'll remember it in a minute. Shoot, what's the name of that authority? It'll come to me in a minute. Well, they actually rule. They inspect it. Not like Anderson County. Whatever it is. I'll think of it in a minute. But in saying that, so we got like, if you was wiring a pier at Lake Hartwell, you got rules you gotta go by. And some of the rules we're gonna be looking at as far as rules, marinas and boat yards in here. Again, farm is one of the things. We really don't have application for that around here anymore, do we? Farm load calculations. May have worked on farm for doing electrical work. But we'll take a look at that. And then lastly will be motor circuits. But in saying that, as far as safety, let's say if you were working around a marina, what would you think about as far as safety?
I guess number one would be just water there, you could drown if you slip or something.
Slip or fall in. So if you're working on a pier, you better, especially if you can't swim.
Tie off or whatever.
Yeah.
Maybe have life vests and.
Yeah, life vest at least available,
Right.
if not on, or if somebody fell in, right, what you said?
Yeah, and maybe a throw rope or something.
Yeah,
like
throw rope.
sandbags.
Lifeline. What else you think?
High tide, low tide, depending where you're at.
It would depend on where you're at. If you're on the coast, yeah. Okay. You need to deal with that. How about anything else? How about groundfall protection? I think that'd be critical. That might be too. Give them a little piece of candy. What else maybe? About a farm?
Equipment, farm equipment.
Mm-hmm.
And they're probably not as used to it like on a job site. You're all, you're always talking about people around you and everything, but they're wide open and whatever, so you probably have to be a little bit careful.
What else maybe? What could you find on a farm that could give you How about a silo? You got to work in one of those. That'd be probably a confined space, wouldn't it? You really get into some safety things, wouldn't you? You probably have to look into what safety regulations would be, particularly if you was in a silo where there could be combustible gas build up, something of that nature. And there are silos around here, so that's definitely a possibility on some of the farms. How about just PPE that you wear? Would it probably differ from on either one of those jobs? Probably not. I'm just trying to think. Again, I think you hit the nail on the head there as far as having some type of throw device or something around. I think as far as the farm, and I think both places, and I think any job, first aid kit needs to be available, but of course, but to me, one of the things on the farm would be animals that you don't want to bite you, like a snake or something, or you don't want to see. I don't want to see a snake let's bite me. So you may have to deal with that.
Maybe make sure you don't get in a bullpen or nothing. If they've got
Yeah.
them around.
Electric fence may be around.
Mm-hmm.
So don't go try going to, to go to the bathroom on it and see if it actually shock you or not. Don't try that at home. Okay. All right. What else? Anything else? How about motors? If you're dealing with motors, what you got to make sure of?
Them grabbing you, make sure you lock out, tag out.
Yeah, lockout, very important, isn't it? Because if you don't, turn it up, somebody turns it on, it's not locked out and tagged. Who's locked out and tagged out? Your boss man or yours?
Mine.
Yours. Your own personal, right? Every lockout tag out should be a personal thing that you have that only you can unlock. Because if your boss man, he might turn it on, right? Don't trust anybody as far as lockout and tag out. It's up to you, your personal responsibility. And motors is a critical thing because you're usually working in a confined space, or I won't call it confined, but an area that, where it could, whatever it happens to be. And if it cuts on, you usually could cut a limb off or something, depending on what you're working on, right? So all those are safety considerations to take into account when you're working in these three areas that we're actually studying tonight. Okay. All right. Anything else as far as safety then?
I'd add motors are heavy most of the time.
Heavy.
especially-
Lifting procedures. You covered that in core, right?
Yeah.
Y'all remember how to lift?
Your knees.
With what?
Your knees.
Yeah, with your knees instead of your back. We covered that in core. Material handling, maybe, like I say, even tying them off, maybe to get them out of an area, right? We studied that in core as far as tying off and using the right tools. Maybe strap lifts or whatever it happens to be, right? Y'all remember that? Okay. Anything else then, as far as that's concerned? All right, let's start then. We don't have a whole lot of material tonight. It's just 3 short sections that we'll go over, and then we'll try to go over some more stuff before tonight's over with. So, anything interesting at work before we get started? Where are you working at?
They got me at Fair Play right now doing some more underground.
Fair Play doing underground. Okay. Digging ditches?
Yes, sir.
Are you? You digging or putting pipe in the ground?
I'm putting pipe in the ground.
Pipe in the ground. So you're not, so your big safety concern would be not being around a trencher or backhoe or what?
It's back there right now.
Backhoe, so there's some precautions to be made in that, right? And what precautions do you take?
Usually up there in front of us, where you can see us.
Yeah. Okay. Of course, weather probably playing a little bit of part in what you're doing right now. Were y'all able to work today?
We got a little stuff done,
Did you?
nothing major.
You been able to work any?
Yeah, I'm still down there at that Dan Foss factory. So it's a different pace than the ground up type stuff, but I guess we've been swapping out equipment and stuff. They got a lot of machinery for, they actually build, valves for like Caterpillar and stuff for their big backhoes and everything. So they got a lot of, homes and different things along those lines. Safety thing is they just have a lot of, the biggest thing is they have a lot of oil everywhere.
Oil.
Yeah, it just gets up in the air, different things, and they've got filters and stuff, so it's not so much breathing it, it's just when you're swapping things out, it could just, you have to make sure you have, we have latex gloves or nitrile, whatever they are.
Mhm.
You gotta put those on just so it doesn't get to your skin.
In your skin.
I mean, if you touch it, it won't burn you, but after a while, you kind of feel
Yeah.
a little weird, so
Yeah.
you always gotta put it on.
Hmm. Good. Good. Other than that, that's about it for that, you know.
Yeah, big stuff.
All right. Okay. Well, good. All right, so on page 37, shore power circuits for marinas and boatyards. Wiring system for marinas and boatyards, designed same as NEC rules. In fact, let's take a gander. It says there, Article 555. Let's take a look at that. We'll probably want to stay there for a little bit. What's the article title, Cameron?
555
Yep.
is titled Marinas and Boatyards.
Marinas and boatyards. Okay, all right. So our rules, we're going to apply there, we see that in the first paragraph. The rules as far as other commercial occupancies except for application of several special, and Article 555 deals with that. The smallest size, I think this is one of these things that you probably potentially need to know. The smallest size locking, what is a locking and grounding type? What is a locking type? What do we say by a locking type? What does it do? What's a locking type receptacle? What does it look like?
That's a twist lock?
Yeah, twist lock.
Around.
You have to have a special, if you got a receptacle also twist lock, you just put any plug in there. You gotta have a matching one, right? Come different wire configurations, doesn't it? Some have a neutral, some don't. Some may be 2-wire, 3-wire, 4-wire, 5-wire. 3 phases of neutral and a ground, couldn't it? So different voltages you gotta come into account. But the biggest thing here, it tells us that the smallest, and that's the key thing, that used for power, provide a shore power for boats is how many amps? How many amps, Cameron?
30.
30. And notice too, it says each single receptacle. How many receptacles is that? Right there on the wall. 4. It is. Okay? That's a receptacle. Okay, so each single receptacle that supplies power to boats must be supplied. Okay, so here's another important thing. So it says each single receptacle that supplies power to boats must be supplied by an individual or dedicated branch circuit with a rating corresponding to the rating of the receptacle. And we can look there, 515.19A3 if we wanted to look at that. Okay. 515, let's take a look at that. 515.19A3, branch circuits. And that's exactly what it reads. Each single receptacle has its own circuit, doesn't it? Okay. And if you look there, number 4 is actually where they find the other part. Number 4 is the same thing. Shore power for boats shall be provided by a single receptacle rated not less than 30 amps. Okay. If you look at A under number 4, receptacles rated 30 and 50 amps shall be a lock. Why would you want it to be a locking type?
You don't want to fall out getting wet.
Yeah, you don't want to fall down and get wet, right? You want it to be a locking type. And look at B, now here's a little, just take it just a little bit further, so anytime you get over 50 amp, you get in like a 60 and 100, what type has it got to be? Pin and sleeve. it'll save a little bit more money, okay? More, even a little bit more, you know, step above locking being a sleeve. Okay. So, but going back to feeders, the feeder or supply capacity required to supply the receptacle depends on the number of receptacles and their rating. But demand factors may be applied that reduce the load. So let's look at 555.12 table. So we got a table there, and it says that 1 to 4 receptacles, what is their demand load going to be?
100%.
Yeah. How about if we had, you know, would we have occasions where there's 30? Sure, we would on a, you know, down in Hartwell, there may be 30 slips on one pier, might be. So if it says there's 30, then how many outlets are we going to have? We got 30 slips, 30 boat slips. How many outlets are we going to have?
30.
30. How many circuits are we going to have?
30.
Okay. But it says we can do what? Derate by what?
70%.
70%, right? So let's take a look at this. So that's 555.12, that's the table. For example, a feeder supplying 10 30 amp power receptacles in a marina requires a minimum ampacity. So here's what we're looking at, the ampacity. Okay. So ampacity, so we got 10, and let's say it says there they're 110 volts. We got 10. Can't remember which one of these were. Probably none of them. 30 times 120 volts, and how much does that equal to? Oh, you got your, no, you got my calculator. How much does that equal to?
36.
36,000?
Yes, sir.
What does that represent? What number does that represent?
VA.
Which is what?
Low amps.
Volt amps. Okay. All right, and now we go to our table. We get how many? 10. It says 9 to 14. We do what? What's their demand factor?
80%
So how do we get 80% of 36,000?
times
Times what?
0.8.
0.8. And that gives us what?
28,800.
28,800. Okay. All right. But this is a 120, 240 volt service. So our voltage, our incoming voltage is 240. And so we divide that and we see how many amps that we would have.
120.
Yeah, 120. And if you look there in your book, that's what it says there. So that's just how to do one of those. This is the minimum. You might want to underline, that's the minimum required by the NEC unless individual watt-hour meters are provided for each shore power outlet. Okay, so that's the minimum. Okay. And a watt-hour meter is just an individual device that actually reads the power use at each station.
So it's like a meter on the back of your house, but.
Yeah, but it's just, yeah, what and it does, it just reads the, but it would have to be read by the owner rather than by the power company.
Right.
So, you know, if you had because what may happen, the owner might use, I don't know, but going back to that example, if he used a total of 300, and we just now said there was how many? 10, right? And so if he just, either one just divided it up, if he didn't have a watt-hour meter, if he had 10, he'd just probably charge each one of them if he wanted to charge them based on that. But if he had a watt-hour meter, he could actually go in and actually read it and find out what total is, because, Joe down here might be having a party every night, and the guy at the end might not use it but once every month or so. So it makes a difference. So he may want to put in a watt-hour meter to help determine the power use. And it's just an inline meter that reads, how much power is consumed, at each outlet is all it would do. But most of them are called a D-line. That's a brand name. But that's about all I've ever seen. It's called a demon meter, is actually what most people call it. Okay, so you put it, they're not cheap. But again, I guess as far as the owner, if he wanted to be able to do that, that would be the way to do that, and that's what they're referring to there. So that's boatyard, that's really it. Just kind of looking, anything else in 555 y'all can take a look at. One of the things, I would say this under 555.13, it talks about wiring methods, and on number 2, it talks about portable power cables, and you see there what type of cable you should be using there. So the extra hard usage portable power cables rated not less than 167 degrees Fahrenheit. Why do you think that? Because what? They're going to be laying out in the sun all the time, aren't they? Listed for both wet and sunlight resistant, and having an outer jacket rated to be resistant to temperature extremes, oil, gas, ozone, abrasion, acids, chemical, shall be permitted as following. And so, pretty strenuous rule there. You can't just go put a drop cord out there, right? What makes sense. Okay. And of course, you know, working around water, you know, always make sure that there's no energized parts when you're working, because, you know, you never know, because the whole fear is getting the water around you somehow energized. And so, you know, one of the safety concerns of working on a pier or whatever it happens to be, especially if you're hard working on a pier, make sure that when you're working on it, it's never an energized circuit when you're out there. Because, again, a lot of times, most of the time, the conduit is, you know, the walkway going out, and somewhere along the way that's going to the ground. And, you know, so, and there's possibilities for that conduit to be close to or in the water, particularly the level of the water level. And so, just another reason that would be very careful, because, you know, you energize that water, you put your hand in there, and all of a sudden you end up in the water and you're shocked and you can't swim and you're there by yourself and they come and find you. Okay. So, just some things to think about. All right, farm load calculations, 3.8.0, Article 220, let's turn to there, 220, Part 5. Part 5, Part B, not point 5, but Part 5. There we go. Page 76 is where I see it. Am I right? Yeah. In a 2014 farm load calculations. And so you got to see here all of, you know, we're talking about some calculations. We're going to see here the table 220.102. We're talking about demand loads, and that's the first thing we see there, is there's a demand factor based on amperage, or what, let's see, dwelling method for calculating farm loads other than dwelling unit. The degrader of the following: all loads that are expected to operate simultaneously are 125% of the full load of the largest motor, or first 60 amps of the load. Next 60 amps of all other loads would be 50%, and the remainder of the other loads is 25. So we definitely need to do one of these. Okay, because it's a little confusing. So let's read in the book. Maybe it helps clarify it just a little bit. This talks about it a separate way. Tables for demand factors provided for use in computing the feeder loads of individual buildings, not dwellings, on a farm. We see that we could go to 220.102, 220.103, and 547 for specific agricultural buildings. Okay. Reading this paragraph, the demand factors may be applied to a 120/240 feeder for any building or load supplied by 2 or more branch circuits. All loads that operate without diversity, that is, the entire load is on at one time, must be included in the calculation of the 100%. All other loads may be included at reduced demands. The load to be included at 100%, however, cannot be less than 125% of the largest motor and no less than the first 60 amps of the total load. In other words, if the non-diverse and the largest load motor is less than 60 amps, a portion of other loads will have to be included at 100% to get to the 60 amps. After the loads of the individual buildings are computed, it may be possible to reduce the total load further by applying additional demand factors. So let's look at this thing here. We got an example. So we got an example here. It says, for example, a farm has a dwelling and two buildings. Kind of typical, maybe a barn, whatever it has to be, storage building. Okay. So dwelling says has a 100 amp load as computed by the calculation method for dwelling. Okay, 100 amps. It already told us that. Building number 1 says it has 5 kVA of continuous lighting load operated by a single switch. And that's just some overhead lighting. A 10 horsepower, 240 volt motor, and 21 kVA of other loads. So let's just take that into account. Building number 2 has 2 kVA of continuous load operated by a switch and 15 kVA of other loads. So let's take a look here at what it says, tells us to do. We're reading there on page 38. Determine the individual building loads and the total farm load is illustrated in figure 11. So let's take a look at figure 11 over here. So let's take a look at this. Building number 1, the lighting load, it says 5 kVA. So that's the first thing, 5 kVA, which is how much?
5,000.
5,000. Yeah, and we're dividing that into what? 240? Gives us how much? It tells you there in the book. It gives us, so this is building number 1. We got 20.8 to start with. That's that one load that they say is continuous. We got a motor. Okay? We got to find out. Let's find out how much the motor is by what table we're gonna go to. Where are motors in our code book? 430. We got some tables in the back. Single phase or 3-phase motor? Single phase. So that's what it says their service is. So we go to 430, 248. In horsepower, what volts?
200, well, 30.
230, right? See that there? 230, because we got the 240. We got to go to the 230 volt column. That's the closest, right? You see that, Cameron? So how many amps is it?
50.
50. If we got a motor, what we always have to do to motor unless it tells us different. Motor's considered to be what? Continuous, right? Unless it tells us different. So we got 50 amps times 1.25 is equal to how much?
62.5.
62.5. So that's our motor load. Let's find me a different pen. All right, so we're good with that so far. Let me find my pen. The investment numbers. All right. So let's just add those together. What we get? 83.3. Is that right? Yeah. But we have other loads, don't we? How much was it? 21 kVA, which is how much? 21,000. We're gonna divide, we gotta get it to amps. We're gonna say, divided by 240, and tell me how much that is.
$87.5.
87.5, so that gives us a total of 8, 10, is that right? No, 170? Is that right? 170.8? All right, but let's take a look at what it tells us to do. And it tells us to take, if you look at the rule, it says take 100% of the motor and the non-diverse load. In other words, that first number that we come up with, this 83.3, it says take 100% of that. So we're going to pull that off to the side, 83.3. Now let's subtract 83.3 from 170, and how much do we get?
87.5.
Yeah, that's right, we get 87. We already did that, didn't we? We know that. But that's not what we do. All right. Okay. All right, let's look at what it actually tells us to do. So we're going to take the next, it actually says the next 60 amps. Okay, you look at figure 11, and look at our rule, it says you take the next 60 amps, and by table 220.102, we're going to take 50% of that. Okay? 50% of 60%, 50% of 60 is how much? 30, right? Okay, so far. All right. Now we already took 60 of this 87.5. So that's, but it says to do what to it? To take what percentage of that in our table? 220.102. It says take the remainder at how much? Table 220.102. So we took, here's what we did. We took 100% of this load. 220.102. Let me just read to you again. Let's read table 220.102. The greater of the fault, all loads that are expected to operate simultaneously, which we said we know that was the lighting, operate simultaneously 125% of the full load motor. So that's how we got this first number of 83.3. All right. The rest of the loads was this 87.5. The rule there says you take the first whatever's, so we've already done this, so we're not fooling with this anymore. So what we got left is this 87.5. So we're really not even worried about this total. Okay. So we got 87.5. It tells us there in that second line, it says take the next 60 amps at 50%. So just the next 60. And so it's always going, that next number is always going to be 30. And then then you just got something left. And that's the last thing. It says the remainder of the other loads is at 25%. So you're taking 25% of 17.5. Y'all get that? You see what I'm saying?
Won't that be 27.5?
Is it? Yeah. Good catch. 27.5. Very good. I did that on purpose to see if you was away. 27.5 times 25% is how much?
Or 6.9.
6.9. Now we just add all three of these together. 12. Help me with my math, Cameron. Been you the math guru. 9, 10, 120. Is that right? Okay. And that's what they come up with. That's building number 1. So number 1. $120.2. All right, that's building number 1. Erase all this. All All right, let's take what we got on building number 2. 2 kVA, 2 kVA. So 2,000, right? It's 2 kVA. What are we going to do with it?
Divide by 240.
Divide it by 240 is how much?
8.3.
8.3. All right, in building number 2, we don't have a motor, do we? It just says other loads. Other loads is 15 kVA. So 15,000 divided by 240 is how much?
62.5.
All right, 62.5. All right, our non-diverse loads, you know, we go back just like we did the first one. The only thing that's non-diverse is this very first thing, this 8.3. All right, so we know that we're going to do it at how much? 100%, right? That's 8.3. Now we take the 62.5. We know we're going to take 50% of 60. So that number again, like we say, is always going to be what?
30.
It's going to be 30. Okay? All right? Why did they come up with something different? Remainder of the first 60. I gotta look at this one, guys. Maybe I'm doing something wrong. I'm thinking about it wrong. Hold on a minute. Y'all help me out here. The remainder of the first 60 at 100%.
Oh, we're supposed to add in all the, because it's the minimum.
Yeah, it's a minimum, isn't it? Okay, okay, all right. Yeah, remainder of the first 60 at 100% minus the 8.3. Okay, all right. So it would actually be, just like it said there, it would be 60 minus 8.3 is what they did there. Okay, it'd be how much?
51.7.
51.7, that's right. 51.7, and now we take the remainder of the other loads. So we had 62.5 minus the 51.7 is how much?
$5.4.
How much is it?
Oh,
Hey.
minus, sorry.
10.8?
Yeah.
And then we're gonna take 50% of that. And you're right, that was how much? 5.4. As you can see there in the book, then what we do is we add all these together now, and it should come up to what? 65.4, is that right?
Yes.
This is building 2. Okay. All right. We see here what they're doing it. The next largest building, if we go back to our, let's see, let me help you find this here. Let's see where we at. Yeah. Look at table 220-103. 220-103. That's for calculating total farm load. So the largest load is what? It's 100%, right? Y'all see that table there? So we're going to take 120.2 is 100%. But what does it say to do to the other building?
75%.
75% of 65.4, and tell me what that is. The 49.1? Is that what you get, Cameron?
Yeah.
Yes or no? You sure? Okay, so that's building number 2. This is number 1, because this is the largest. It's at 100%. Number 2 is how what percent? 75% per that code. So we add these together. But now what do we still have left? We got the dwelling, but it just told us what that load was, didn't it? It says it's what? What did it tell us their dwelling was?
100 amps.
100 amps. $269.3 amps. Let's take it one step further. Well, it actually told us there, but let's confirm what it said. Let's go to the 31015B16. Copper conductor. What column we going to use? 75. And let's see what wire size we would be using for that.
$400.
400?
Wait, my bad. 300.
300. Because 300 is good for how many amps?
300. $285.
Okay. All right, 285. All right, let's take it a step further. Let's do something. We got 300. So we're going to have, and it's already done it for us. All right, so let's write down 2 300s. Okay. Let's write this down. So we got 2 300s. Y'all with me right now? And we're going to say that's THHN. All right. All right, it tells us here, and we're not going to go through the calculations, let's look in our book. It tells us our neutral load is 206 amps. 206 amps. So we could derate our neutral, couldn't we? So let's go to the same book, let's go to the same table there, and tell us what our neutral size could be. 4 off. Well, we got 2 in here because it's single phase, right? How about a ground? How are we going to determine a ground? We're going to go to 250, aren't we? Let's see which table we go to.
Is it 250, 66?
I don't know. You tell me. You think it's 256 when it says a grounding electrode conductor for alternating current systems? Or do you think it's, let's turn over to the next one and kind of read about it and see. Minimum size equipment, grounding conductors for grounding raceway and equipment. Which one do you think it would be?
Surface entrance, 250-66.
You think so?
Because that's what we're.
Size of the largest ungrounded surface entrance conductor or equivalent area. But now grounding electrode, we're actually, let's think about it. Grounding electrode means we're going to take it to the building steel, we're taking it to a ground rod, and not necessarily the same thing. Let's go over, let's just kind of look. Let's go over to 250-122 and just kind of look at it. Minimum size equipment grounding conductors for grounding raceway and equipment. Rating or setting of automatic overcurrent device, because we're going to size. So now we would have to go, we actually need to determine our overcurrent device before we do this ground, don't we? We're going to go to 240.6 and we're going to find that the common is how much? Go to 240.6 and you see that your common overcurrent device is going to be what? 240.6. We got 269 amps. What's our overcurrent device going to be?
300.
300. So now we go to table 250-122 and say we got a 300 amp device. We're going to put a what size wire in there?
Number 4.
Number 4. All right, now we got these wires here. Let's figure out what size conduit we're gonna put it in. Where we gonna go to do that? How about table 9? Right? Chapter 9, I'm sorry. Chapter 9. But they're not all the same size wire, are they? But I did tell you they're all THHN. So let's find out what we got to do. THHN. Table 5. THHN. Let's determine the inches square, approximate inches square for each one of these wires, right? Is that what we're going to do? So for, we said a 300 THHN, what is my inches squared? Y'all tell me. I'm on about page 763, Cameron. Chapter 9, table 5. Chapter 9, table 5. Let's look it up together. Page 763. A 300 THHN. The area inches squared is going to be what?
0.4608.
0.4608. You see that, Nate? So that's 1. How about a 4 all?
0.0824.
A 4 all?
Or, sorry, I was thinking 0.3237.
Yeah. And a number 4?
That's the 0.0824.
What do we got to do this first one?
By 2.
We got to double it, so let's just add another one. 4608. Y'all add all that together and tell me what you got. How much you got, Nate?
I kind of messed up on the buttons here. I forgot to put my decimals in.
Cameron, you got it yet?
I got 1.3277.
77. All right, now let's say we're going to do it in EMT. You agree with that, Cameron? You agree with that? We're going to put it in EMT. We're still in chapter 9 in the back. We're going to find how much fill we can put in an EMT conduit, right? And so on page 757 in your code book, table 4, article 358, electrical metallic tubing. Which column are we going to use? Over 2 wires, 40%, 60%? Which one are we going to use? 2 wires, 1 wire? What are we going to use? Which column are we going to use?
Over 2 wires.
Over 2 wires. And we got 1.3277. And so what size conduit would we be using?
Two and a half.
2.5? Well,
I mean, you can almost get away with.
I agree with you. Literally, you could use a 2-inch, couldn't you? But I'm not going to put it in there, are you? I'm going to put it in a 2.5. I agree. Even though technically you can put it in a 2-inch, but I'm not doing it because I'm going to have to pull the wire. Okay? So, let's go back to this a minute. Why did we use the number 4 wire? Why did we use that table? Let's talk about that just a minute. Grounding electrode, let's think about that. Really, when we got that first table, grounding electrode, what we're thinking about is, you know, the ground that's going to my water pipe, to my ground rod, my building steel, that's grounding electrode. Whereas my other, and matter of fact, and how was that actually sized? $250.66. It was sized on the other wire sizes, wasn't it? Whereas the other table bases it on what? $250.66, table $250.66. We're basing the grounding electroconductor based on what?
Service entries.
Well, on the wire side on 250.66. But on 250, what was it, 122?
That one's the overcurrent device.
Yeah, the overcurrent device, which we have to determine from what? From our what? From our total load, right? And then we have to go and we have to find what actually overcurrent device we can actually use based on that ampacity. Because let's think about it. Why does it make sense to use that table versus the grounding electrode? Because where's that wire going? In that same conduit with this wire, right?
Right.
And this table is based, you know.
The overcurrent. So it's coming in from the service to like the meter, and then we're going from the meter to the buildings.
Yeah,
And so that's why we have to click the ground in there.
that's right. Yeah. Makes sense? It's a little confusing. I actually, on mine, I actually put a note on 250.66. I kind of wrote in a note to myself just to help me remember it. I actually put building steel, water pipe, you know, I just kind of wrote in down at the bottom, you know, ground rod. That kind of helps me remember to use that table for that.
Because you're not gonna bring the ground in from the service. You're just going from
Right.
straight from there to the.
You're going to come off your MDP or whatever it is, you know, and you're creating your ground, right? With your triad or 2 ground rods, whatever you got to be, you're creating that ground there at your, you know, the power company's not bringing in the ground. You're creating the ground there. Make sense? Y'all want to take about a 5-minute break? What time is it?
6:46.
Yeah, let's take about a 5-minute break. And then we'll do motors, and that'll be it as far as the book, and then we'll go over some things. All righty. Let's finish up this part of the book. Last thing is motor circuits. Page 38. 2 or more motor circuits, they can be connected to the same feeder. We know that we're going to derate if we do that. Matter of fact, we're going to take, the rule is, if you see there, the rule is to compute the sum and then 25% of the, and I'd underline that word, the largest motor. In other words, if you had 2 motors that were the same size and they were the largest, you're only going to take one of those and do 100. Like if you had 2 7 horsepower and 1 4, you're going to take 25% of one of the 7 horsepower. Make sense? Okay. Note the exceptions regarding motors with duty cycle. Duty cycle means that it, you know, it has certain times that it would work. So if you see here, it says care must be designing circuits such as this prevent several motors connected to the same circuit from starting at the same time. If not designed correctly, severe voltage dip affect the operation, and not only that, it can affect the motor. Burn it up. So we got an example here. So the following 3-phase 208-volt motors are supplied by the same feeder circuit. So we got 1 feeder circuit feeding 3 motors. So we're probably going to go out there and what we're going to do. What do you think we're going to do in the field? We're going out there with a feeder circuit. We're going to feed 3 motors. What's probably the first thing we're going to do when we go out there? What we're going to say? before the junction box? No. But we're probably gonna set, because we're probably gonna put what on each one of these motors?
Disconnect.
Disconnect. So probably what you think we're gonna do? How we gonna what we're gonna feed 3 motors on?
Gutter box?
Yeah, the gutter box, right? We're gonna tap them in that gutter box. Agree with that? So, in saying that, we see here, we got a 20 horsepower. What's the other one? 10 horsepower? And a what? 5 horsepower. So they're 3 phases, so we gotta go to 250, find out our loads. 430. 250 is ground in there. 430, 250, I think it is. I think that's where I get my 250 from. 430, 250, and we gotta find out the load for each one of these. Tell me how much a 20 is. 208 volt, 3 phase. Equal 430, 250.
59.4.
How about a 10?
30.8.
And a 5.
16.7.
Now what we gotta do?
225 of the 20 horsepower.
And how much is that gonna equal? You see why we did 125%, right? Because you gotta take 25% more of the largest motor. So we simply just multiply it times 1.25.
74.25.
74 point what?
25.
Now what are we gonna do? What we gonna do, Cameron?
Add them all together?
Yeah. And tell me what you get. How much you got?
121.75?
121.75. Now, let's go to 31015B16, find out what wire size was used. THHN. Or THWN is what the book actually wants. Doesn't matter. We're still gonna use 75-degree column. Number one, very good. Number one. I want Cameron to get there and agree with us. Number one. You agree with us, Cameron?
Yes.
Okay, number one. All right, let's do review questions in the green. Let's go over these. All right, number one, the feeder load for a show window that is 35 foot. What is their answer going to be?
A?
A?
I had B.
You got B? All right, how did you get 7,000?
It's 200 vol amps per foot, so 35 times 200 would equal 7,000.
How did you get the other, Cameron?
I thought I read it wrong.
Now, let's go to 3.1.3 and see if we think Nate is right. 3.1.3.
Okay.
Let's look at the rule and see what it says. Three point one point three says show windows what? How many, what per linear foot?
200.
200. 200. So per linear foot. So B is the correct answer. Okay. B is the correct answer. Now, number 2, the general lighting load for a hospital per NEC 220.12 is what?
I had B.
B? Okay. What you got, Cameron?
I got B.
You got B? And we would find that simply by going, it says to go to 3.2.0. Okay. We can also go to the code book, can't we? And find it under the table that tells us to, can't we? Okay. Oh, that goes to 3.2.0, I'm looking. That's what it says, oh well. Go to the code book, we'll look it up and find it, right? So both of y'all got it right, so. On a 15,000 square foot office building has a minimum lighting load of what? $15,000 square foot office building. Where we're gonna find, what table we're gonna find for a lighting load? Where you gonna go? $220.
144.
Hmm. Yeah, 220 point what, 12?
Mm.
We're gonna find that an office building, the VA per square foot is how much?
3.5.
Yeah, 3.5. So we're just gonna simply do 15,000 times 3.5? Is that what y'all got? Which was D, 52,500? Is that right?
Mm-hmm.
No, is that come to that? Is it?
I got 52D, 52,500.
Yeah, 52,500, okay? 15,000 times 3.5 comes to that. You agree with that, Cameron? Huh? You get it right?
No, sir.
No? All right, so to do it, have you got one of these questions on your test now? Make sure that you find under table 220.12 the correct general lighting load. And like this one is listed in the office building, you go over to volt ounce per square foot and you see that it's 3.5. You take that 3.5, you multiply it times the square foot to come up with the total volt ounce. See that?
Yes, sir.
Okay. All right, per NEC, let's go to 220.56. Per NEC 220.56, so we will look at that table there. The demand factor for kitchen equipment other than dwelling units. The demand factor for 8 pieces of commercial equipment is what?
65%.
65%. Yeah. Okay. The demand load, lighting load, for a 10,000 square foot motel with no dining room or ballroom is blank. We're gonna go to our table again, right? We're gonna find We're gonna find the total is how much? What it tells us to do?
Times by 2,
By 2, which gives us what?
20,000.
20,000, right? Okay. All right. But now let's go over to table 22042. I'm trying to see if I agree with him or not. 20,000.
I got 50% demand factor on that one.
Yeah, where did we find that at?
22042, and then down.
Oh, yeah. Hotel, yeah, 50% automatically, isn't it? The first 20,000, yeah, I'm sorry. Yeah, so the first, up to 20,000 is 50%, isn't it? You see that, Cameron? I was missing it too. Table 22042, bless you. You go under hotels, motels, including apartments without provisions for cooking, and you go to the first 20,000 and 50%.
Okay.
See it?
Yes, sir.
You have to go to 2 different tables. First table you gotta go to, you gotta find your lighting load VA, which is 220.12. Then you gotta go to your second table, which actually gives you the demand factors based on your total load.
Okay, so it'll be 10,000.
Yeah, 10,000. All right, a school has 150 kVA air conditioning load and a 200 kVA heating load. The value to be used when sizing the combined connected load is blank. The smaller of the 2 loads, the larger of the 2 loads, 125% of the larger load, or the sum of both loads. What do we do? How about 3.6.0? Let's look and see what it tells us to do. You may know what to do, but let's look and see what it tells us to do. If you look at the second paragraph, it says if both air conditioning and electric space heating loads are present, only the what?
Larger of the loop.
The larger of the loads. So what would be the answer then?
B.
Large, B.
B. Okay. All right. Let me reply to this right quick. Next one. A feeder supplying 6 30-amp shore power receptacles requires a minimum of what? We just did this one. Let's go back to our book. We got, matter of fact, we got to go to what? What table we got to go to? 555. Wasn't that marinas? Find our table there. It says we got 6 30 amps. What are we going to do? 30 amps times 120 volts is how much?
21,600.
How much?
Oh,
Yeah.
sorry. Well,
You just went ahead and doing it all.
Yeah, sorry.
21,600, because you got 6 units, yeah, times 6. Okay, 21,600, you agree with that? How'd you get that, Nate?
Well, it was 6 times 3, which would have been 180. And I was assuming that it was 120 volt outlets. They didn't say.
They didn't say, but I think so too.
So 120 times
Yep.
volts times your amps would give you 21,600.
Okay, 21,600, and now their table in 555.12 says that we have 6, our multiplier is what? What is their multiplier? Cameron, what's their multiplier?
555.12,
Yep. We got 6,
90.
90%. So 21,600 times 90% equals what? Is that what it equals to? 19,440? Is that what you got, Cameron?
Yeah, that's what I got.
Okay. Which of the following is true when calculating farm loads? We just kind of went over this. Only the motor loads are counted. Only the non-motor loads are counted. At least the first 60 amps must be counted at 100%. All loads are counted at 75%. What's true? Which one is true? We just went over this. Which one is true? Nate, which one is true?
C, at
C.
least the first 60 amps.
Yeah, at least the first 60 amps must be connected at 100%. Okay. And number 10, a 10 horsepower motor, 30.8 amps, and a 15 horsepower, 46.2 amps motor are connected to a 3-phase 208 feeder. The total load is what? So we got 30.8. And how much?
46.2.
Is that all we're gonna do? 77 amps, is that right? Is that right, Nat, Cameron?
I guessed on that one.
What we gotta do, Nat?
Multiply the 46.2 times,
Times what, Cameron?
125%.
That equals to what? How much?
57.75.
Now what we're gonna do? Now we're gonna add them up, right? Is that right? Yeah, 88.55, which is C. Please remember, if you got more than one motor, the largest one, when you're doing a feeder, you gotta do what? 125% of it.
And then you add it all together.
Yeah, then you add it together. Don't forget that part, because they would probably give you the other answer, which they did, if you just added them up. All right, review questions. Let's take a look at these, just a little bit. I say next week, we're gonna have our test. So, let's take a look at these and see. And I'm gonna try to help you get there, and we're gonna see if we can answer them together. All right, a feeder circuit supplying a lighting and appliance panel board is sized by adding blank of the non-continuous load, and we may answer this one without even looking it up, guys. Look at what it says. Blank of the non-continuous load and blank of the continuous load. What are we gonna do?
D.
D, 100% of the continuous, 125% of the non-continuous 100%, 125% continuous. Okay, D, all right. So, number 2 then, what's the ampacity for each of 8 number 2 THWN conductors carrying installed in a single conduit? Okay, let's go to 1.1.1, and it's going to kind of tell us what to do. Continuous to raceway field. So what we're going to do, so we got raceway field. Don't we have a table for raceway field? Let's go to 315. Let's go to around 315. B3A in your code book. Page 160 in your code book. Well, let's find, first of all, let's find a number 2 THHN. Let's find out how much it's good for. 1. A number 2 number 2 THWN is good for how much? Is it 115 amps?
That's what I got.
Now by table 31015B3A, the total number of conductors is how many? 8? So what's their multiplier gonna be?
70%.
Yeah, see what that comes to.
80.5.
Okay, 80.5, which happens to be B, right? Y'all understand how to do that? Nate, Cameron, you got it? Know how to do that? No?
How do you find 80.5?
How do you find what?
I know the demand is 315B, 3A, but how did you get to TH80?
310, 15, B16, page right over there. You got a number, it says you already, it tells you what your wire is. It says it's number 2, THWN. 75-degree column is THWN, you see it there?
Yes.
Copper. And you go down number 2 and it's good for what?
115.
Yeah, that's where I got that from.
Okay.
Then you take 70% of that, right? Okay. So you go, and y'all can use your code book on the test now, so you need to understand where this stuff's at in your code book. That's why we're really taking our time on this and going over this slow. So, and review your code book between now and next week when you do your test, because you need to know where this stuff is at. I'm not going to be able to tell you, okay, when you do these calculations. Okay. Number 3, what is the rating of a 250 THHN copper conductor in an ambient temperature of 101? Well, first of all, let's find out how much is just 250 is worth before we do anything to it. So 250 THHN, okay, is how much? $250 THHN is how much? $290?
Yeah, 290.
Now we're talking about temperature. It says it's how much? 101 degrees Fahrenheit? All right, let's go back. Now there's a table in our code book. It talks about temperature, and it's found on page 158 in your code book. 158 in your code book. And we see that 101 degrees Fahrenheit, what multiplier do we have? On 90 degree, we use 90 degree because that's what we used right there, right? So it's what? 0.91? Let's see what we get if we do that. 290. Where's my calculator? $263.9. All right, now why did we do that? Why did we use, let's think about this thing a minute. Want you to understand how to do this. And why did we use 290? Why did we use the 90-degree column and not the 75?
So that's what a wire is rated for?
Because that's what the wire is rated for. We're not trying to do any kind of load or anything like that. That's what the wire is rated for. You go, when you're using this, you go into the actual column, the 90-degree column, because that's where we find THHN, isn't it? That's what it's rated for. Now it says the temperature, we go to that table on page 156. Why did we use, you see how to find 101 degrees, Cameron? Page 156 in your code book. No, I'm sorry, 158. I ain't got on my glasses. Page 158. There's a table there. One side is Celsius, the other side is Fahrenheit. So you're trying to find Fahrenheit, which is 101.
Yeah.
Now there's 3 columns, 60, 75, and 90. Which one are you going to use?
90.
Why?
Okay, that's what we use.
Well, we use on a wire, so it's what? Point what?
91.
0.91. That's how you do one of those. Don't remember on this, you're not going by your over 100, over under 100. You're going by the actual rating of the wire based on what type of wire that it is. The other thing don't get confused on is make sure you look at Fahrenheit and not Celsius, or whatever they ask you for, okay? All right, number, let's see, I'm kind of check these off as we go, because we're not gonna get through all of them. So number 4 is where we're on 4, yeah. What is the rated ampacity per phase for 6 3-aught THHN copper conducting carriers with 2 conductors per phase parallel and all conductors installed in the same conduit? Okay. Let's go to 3-aught THHN. 3-aught THHN is good for how much?
225.
225. All right, it tells us we've got per phase 6. What is the rating ampacity per phase for 6 3-aught carrying conductors with 2 per phase parallel and all conductors installed? That's kind of confusing, isn't it? For per phase for 6 number 3-aught copper current carrying conductors with 2 conductors per phase and all conductors installed. How many wires do we think they are? If you read that, how many do you think they are?
I think there's 6. And
You think there's
one
6?
conduit.
Okay, that's what I'm thinking. Let's look and see if we come up with the right answer by doing that. I agree, but I'm not sure that's right. 225 times 0.8 is what? Are we doing 0.8? Excuse me just a second, let's see who this is. Hello? Oh. Hello? Hello? 266.8, 225.8, is that what we got?
180,
How much?
180.
180? Is that one of our answers? What?
Well, then you got 2 in parallel.
Oh yeah, we got 2 parallel, don't we? Okay. 180, and then what we're gonna do then?
Multiply by 2.
Yeah, times 2, which is 360, which is D. But parallel means we got what? We got 2 of them, right? And it says we had 2 of them parallel. We could have more, but you're doubling it because you said you had 2. Okay. Make sense, Cameron?
Yes, sir, it does.
Okay. Let's do a couple more. We're gonna call it a night. Number 5, the voltage drop percentage for a panel feeder with a non-continuous load of 180 amps using 3-aught THWN conductors at 480 volts, 3-phase, and a length of 248 feet is blank.
A,
How much? What is it?
1.23%.
How'd you get that?
I remember it.
You remembered it.
Yes, sir.
Okay. How we gonna get there though, if we don't remember it?
That I don't remember.
That you don't remember?
Yes, sir.
What number are we on? Number 5. Alright, so square root of 3 is what? 1.732. Y'all agree with that? How long is it?
248 feet.
248 feet. We'll come back to that other in just a second. How many amps? Well, how many amps is it?
180.
180. Okay. We still got to get the diameter of the wire here in a minute. Okay. All right, we're going to divide it by 1,000. We got to find out the wire, so we got to go to. I'll just take. We would go to where to find the diameter. We got to find the diameter of the wire is how much? Where we're going to find the diameter of the wire?
Chapter 9, table
Chapter 9, table
8.
5 maybe?
5.
No, that might be table 8. I don't know. Let's
Yeah,
go back.
it's table 8.
see what 3-aught is. 3-aught THWN.
You said table 8?
Table 5, I think it was, wasn't it?
Well,
Or it might be table 8. Yeah, I think it is table 8.
Cause it's the cross section of the copper.
Yeah.
Not,
That's right.
Yeah.
How much is it?
I got 167,800, circular mills. 167,800.
Now, we're not looking at let's look, we're actually looking for resistance.
Oh, resistance.
Sorry.
.0766.
0.0776, is that what you said?
.0766.
Is it 66? Alright. Okay. Alright, we'll multiply all this together, because this is square root of 3, the footage, the length, the resistance. Okay. Multiply all that and see what you get. How much you got?
59.22.
How much?
59.22. It'll be 59.224423.
Is it 59?
I got 5.9.
5.9? Yeah,
And the rest of it, no.
close enough, 5.92 volts. By the time you do this, you missed something there somewhere, Cameron. Okay. That's how many volts drop it is. But they're asking us actually for a percentage. So to get the percentage, what was our voltage?
480.
So we're trying to find out how much this is of this, right? So you take 5.92 and divide it into 480, and you get what?
What he remembered?
Yeah.
1.23.
1.23%. Cameron,
Yes, sir.
you just got very lucky. Very lucky, is all I got to say. Don't put that for, and if y'all wanted to figure out, let's go to, if you wanted to go back quick, guys, 1.12 in your book is an example of this. So you may want to study this. I can't remember if we got to or not. 1.12 talks about voltage drop, and it gives you that formula. See formula number 1? That's where we got that from. Formula number 1 there on page 4. There was 2 different formulas because that's what we had. Okay. So that's where we got number 5 from. Okay. All right, let's do number 6, and we're going to definitely call it tonight. Okay. Number 6. What's required size of THHN copper for a feeder serving 2 208 full-wire 3-phase 75-degree branch circuit panel boards, one with a continuous load of 150 amp and the other with a non-continuous load of 180 amps. Okay. So 180 amps was what? Non-continuous load, right? How much was the continuous load?
150 amp.
And what are we going to do with it? What are we going to do with continuous loads every time?
Times 1.25.
Yeah. What does that equal to?
$187.5.
And what does those added together equal to?
$367.5.
367.5. Now it's asked us to see what wire size it would be, where we're gonna go to. This should be automatic.
310, 15.
310, 15, B16 every time. Find wire size cameras, you go in there every single time. Why in the world you don't get some taps, I don't know. It would cut your process in half of taps. 310, 15, B16. There's a tab for it. You got tabs, Nate?
Yes, sir.
Thank you. Camera bays and tabs. 310, 15, B16. We're gonna look at it and we're gonna see, based on that, now we're gonna go to which column?
75.
We're gonna go to the 75-degree column, and we're gonna see that what wire side would we use?
500.
500. 500. Okay. I'm done. Y'all look done. All right, so I want you to try to do the rest of these, 7 through 20 for homework. And, because this will help you. 7 through 20 for homework, we'll go over them when we get into class next week, and then we're gonna take our test. I've told you what to review for, you know what to review on. I told you that last week, right? Right? Okay. So we'll finish the review next week, then we'll take our tests, and then we'll review the test, and that's what we'll do next week. Okay, sound good? All right. I'm good if y'all are. Calculations on that test, guys, y'all study these calculations, okay?